So, welcome to this module. The last module what we have seen? We have seen how we can design the process flow for a MOSFET, right, and I hope you have seen that lecture and you now have a basic idea. If you are given a MOSFET and if you are asked to design the process flow for fabricating the MOSFET, you can fabricate the or at least process the design, alright. And also with the earlier lecture, now you are at least able to design the process flow for several devices, right. It can be a biosensor, it can be a gas sensor, right. Same way it can be a micro heater, right. So, the things becomes very easy once you learn the process flow and the recipe, correct recipe for the particular process flow. Now, in this module let us see further how can we understand the characteristics of a MOSFET and how we can apply the MOSFET as a current mirror, okay, that will be looking at. So, if you come back to the screen, what you see is the MOSFET that we have already seen, the schematic, which is your n channel enhancement type structure, and we already know n channel enhancement type structure has a p type substrate, right, is a substrate, and then you have source, you have drain. It can be like this, it can be in a different way also. This same thing does not matter, it does not matter whether you consider this as source, you consider this as drain, does not matter, okay. So, it has source, it has drain, it has gate, right, and then we have to understand how this MOSFET will operate, okay. So, let us understand the construction and working of this MOSFET. The we know that what are active devices? The active devices can control the flow of electrons and eventually the current. For example, BJT, JFET, MOSFETs, these are all active devices. Passive devices are which cannot control the flow of currents and or flow of electron, and these are diode, capacitors, right. So, these are examples of passive devices. When we discussed about MOSFET or when anyone discusses about MOSFET, generally the MOSFET is divided into two types. One is your depletion type MOSFET, another one is your enhancement type MOSFET, okay. And then when we talk about depletion type MOSFET, then we further understand that there is a n channel depletion type, there is p channel depletion type, there is n channel enhancement type, there is p channel enhancement type, okay. Now, when we talk about depletion type MOSFET, the channel is already there in the beginning. When you talk about enhancement type MOSFET, there is no channel between source and drain. There is no channel between source and drain. What does that mean? That right now what we have seen this structure. This structure, is there a channel? Is there a channel? There is no channel. There is no channel. So, this is your enhancement type MOSFET. Okay. But if there is already existing channel between the source and drain, if there is a channel existing between source and drain, then it is a depletion type MOSFET. Okay. Then it becomes depletion type MOSFET. So, from the beginning, without applying gate to source voltage, without applying drain to source voltage, if there is a channel in the beginning, it is a depletion type. If there is no channel, it is your enhancement type. Okay. So, remember these things, okay. You already know the symbol for the depletion type, n channel depletion type, p channel depletion type, enhancement type, n channel enhancement type, p channel. Now, the basic difference here, if you see here, that the drain, gate and source, these are not connected, right, means there is the channel is not there, in depletion type the channel is already existing, okay. So, easy way of understanding whether is enhancement type or depletion type is when you are given the symbol for the transistor, then you can understand if there is a break like source, drain and gates are source and drain is not connected, it is your enhancement type. Source and drain is connected in this particular fashion, you can see here, right, then it becomes your depletion type, because channel is present in depletion type, channel is absent in the enhancement type. This is another way of understanding the or recognizing the type of MOSFET. Now, you see substrate body, right, substrate body is p type, and if I diffuse or if I dope the n channel into the p type, then this becomes my source and drain, this becomes my source and drain, and because there is a p, because there is a n, there will be creation of this depletion region, there will be creation of depletion region, as we can see from the schematic, from the slide. And you can see here there is a connection for the base or is connected for the substrate, connection for the base, connection for the substrate, connection for source, connection for drain. Now, if the substrate is p type, source and drain are n type, then this n channel, and the substrate is n type, right, source and drain are of p type. What does it mean? If my substrate, that is my silicon, right, my silicon, if my silicon is p type, then my source and my drain, this both are n type. If my channel is n type, means if my substrate is n type, my source and drain are p type. Okay, that is another way of understanding it, another way of understanding it. Okay. So, see n type and p type I am talking about substrate, okay, not talking about the channel, n channel MOSFET is different. Okay. Now, enhancement type MOSFET, if we talk about enhancement type MOSFET, let us see how the enhancement type MOSFET looks like, how the enhancement MOSFET looks like. So, what we see here is, you see here, this is the substrate, the substrate is p type, right, that means the majority carriers are holes, right, minority carriers are electrons, mobile charge carriers equals to immobile ions, right, that is why the charge neutrality would be maintained, easy, right. What is that? P type, majority are holes, minority are electrons. Now, for mobile charge carrier is equal to the immobile ions. So, that means your charge neutrality will be maintained, correct. Now, you have source, you have drain, you have connection for source, you have connection for drain, you have connection for gate, you have connection for your base or substrate, right, and you can see here the gate oxide is only 100 nanometer, 1000 angstrom. So, here the gate oxide is extremely thin, extremely thin. This is your enhancement MOSFET, because you cannot see any channel present between your source and drain. There is no channel between your source and drain. Okay, easy. So, let us go to the next slide. Now, whatever I have told you earlier is same thing. Enhancement type transistors, you can see how the enhancement type transistor looks like, how the depletion type transistor looks like, how the enhancement type PMOS transistor looks like, how the depletion type PMOS transistor looks like, and then we will also see the complementary metal oxide semiconductor. Okay. So, let us first talk about enhancement type NMOS transistor, enhancement type NMOS transistor. So, if you see this particular schematic, what does it show? It shows that you have a substrate, and the type of wafer is p type, in that you have diffused n channel source and drain, right, and then you have a gate separated by a thin layer of oxide, and gate is a metal. So, the contact is a metal, right. So, now what will happen? There is a metal here, there is conduction in this region, and this is your oxide, right, this is your oxide. That means, it looks like you have two conducting plates separated by an insulating material, and this insulating material is your silicon dioxide. It looks like when we see this particular figure, this one, it looks like if you see gate right, and if you see this body and if you see this oxide, looks like there is two conducting plate separated by a dielectric material. So, when you have two conducting plate separated by the dielectric material, it becomes your capacitor, it becomes your capacitor, right, that is the definition of a capacitor. So, in this particular case, you see the charge carriers, if I apply VGS that means like this, and apply negative, gate positive, gate is positive, source is negative, then in this case my gate would be positive, source would be negative, right, and I am connecting this thing to the source, I am connecting my substrate to source, right. Again let me just write it down here, so that you can see clearly my source is negative, gate is positive, okay, applying source to gate to source voltage or source to gate voltage, and I am connecting my substrate to the source, I am connecting my substrate to the source. In this case, this will be the connection in which I can see that there is a positive charge, there is a negative charge. How it comes here? Because when I apply positive charge here, then the minority carriers from the p type, that are electrons present, that will come here, right, towards the gate. It will get attracted towards the gate because gate is positive with respect to substrate, right, with respect to substrate, gate is at positive voltage. So, that is why negative charges would be like here, and formation of channel would be there, okay. Now, there is a question, how negative charge is accumulating in the substrate? Negative charges are accumulating substrate, because you see here we have given a detailed understanding. Here you can see the detailed understanding. VGS, when you increase, on uncovering of negative immobile ions takes place by pushing holes near the body, right. Uncovering of the electrons, that is here, will take place, right. Negative immobile ions is your electrons, by pushing holes near the body. In this case, initially electrons accumulates near the oxide, you can see the electrons accumulating near the oxide, right. When your VGS is increasing, that means your gate is more positive than compared to source, your electrons, that is the negative immobile ions, will start accumulating towards the gate. These are minority charge carriers, okay. Now, later VGS, if we keep on increasing VGS, it causes uncovering of negative immobile ions, right, which forms the channel, finally it forms the channel. If I keep on increasing VGS, then lot of electrons would be accumulated here, and then it will form a channel between my source and my drain. There will be formation of what we call channel. When my VGS, I keep on increasing the gate to source voltage VGS, okay, easy, right. This process, when this channel is formed on increasing VGS, this process is called inversion, right. We have all studied this, if not, this process is called inversion, got it, easy, okay. Now, let us see further, okay. Now, VGS is greater than 0, that means inversion is there. Conductive channels formed between source and drain, right. This is conductive channel is formed between source and drain, you can see, and in this case, when VGS is used instead of VGSS or VGB, right, we are using always VGS. Why we are not using VGSS? Because here see substrate is there, right, here the substrate is there, here the source is there, right, and we have connected the substrate and source like this, we have applied negative to source, positive to gate, but we always say VGS, we never say VGSS or VGB, because source and substrate are connected internally. I have told you earlier also, I am repeating it here, source and substrates are connected internally, that is why you will find MOSFET ICs with only 3 terminals, source, gate and drain, source, gate and drain. Okay. So, when this means that VGS increases, channel width also increases, correct. If I keep on increasing VGS, my channel width will also keeps on increasing, my channel width will also keep on increasing, right. So, when VGS is increased below greater than particular voltage, my current ID is sufficient to for when my VGS is greater than particular voltage, this voltage is greater than VGS is greater than particular voltage, what will happen? There will be sufficient flow of current, sufficient flow of drain current, sufficient flow of drain current. Why? Because now my electrons from source can reach to drain using the channel here, using the channel here. So, there can be flow of current ID, there can be flow of current ID, right. So, this particular voltage, right, above which when VGS reaches is called your threshold voltage, alright. So, threshold voltage, the VGS should always cross, in this particular case we are talking about n channel MOSFETs, n channel enhancement type MOSFETs. When VGS is increased greater than threshold voltage, then only I will be able to see that there is a sufficient flow of drain current. Okay, easy. Okay. Let us see what is VT. VT is your threshold voltage that results significant amount of current to flow from source to drain, right. This is what we have seen, that is a minimum voltage that the VGS has to cross, so that we can see that sufficient amount of current is flowing from source to drain, right, and this is your current ID, this is your current ID. Okay. Now, if I have VGS greater than VT, then what will happen? My ID will keep on increasing. What is the case? Here the case is, you see, VDS, right, drain is positive with respect to source, VGS, gate is positive with respect to source. Okay. So, what will happen? When my gate is positive with respect to source, drain is positive with respect to source, the drain will start attracting the electron from the source, but before the formation of electron, before the flow of electron can happen, initially there is no channel, but because the gate is at positive voltage compared to the source, that is why there is a formation of channel, and this formation of channel will help the electron from the source to move towards the drain, creating in the drain current ID, So, as I keep on increasing VGS, my ID will keep on increasing. So, another one is why we have to connect this source to substrate. What is the reason of connecting source to substrate internally, right. So, another reason of connecting source and substrate is to avoid too many bias potential, right. If I do not apply, so if I do not connect internally source to substrate, I have to apply a bias potential. So, to avoid this so many bias potential, I am using I am not applying, I am internally connecting, the source and substrate, alright. Or you can see that when you have a IC, the source and substrates are internally connected to avoid too many bias, potential. Okay. Next is, if we have to find the effect of voltage VDS on depletion layer, what will happen? The effect of voltage VDS on this depletion layer, let us find out VGD, right, because we have to understand what is the difference in the voltage that is developed between gate and drain. When we have to find the effect of voltage VDS. So, if I want to find the effect of voltage VDS on depletion layer, I have to find what is the voltage across gate and drain, alright. So, if I take this example, if I take this schematic which is right in front of you guys, and I want to find this VGD, then I had to use Kirchhoff voltage law. So, when I use Kirchhoff voltage law, what will happen? So, we go from here, right, Vg from here, okay, Vg, right, then we go here, this one minus Vgs, then we go here in this direction, all right, from here we go this way. So, Vg minus Vgs plus Vds equals to Vd, right. So, Vg minus Vgs plus Vds equals to Vd. If I rearrange the term, we have Vg minus Vd equals to Vg minus Vd equals to Vgs minus Vds. What is Vg minus Vd? Vg minus Vd is nothing but my Vgd, right. That means my voltage at the gate minus voltage at the drain is nothing but my voltage across gate and drain. That is why I can find the relation between Vgd and Vds, that is Vgd equals to Vgs minus Vds. This is something that I have found, alright. Now, I want to consider 3 different cases. Let us see the first case. First case, when we consider case 1, Vds equals to 0 volts, Vds equals to 0 volts. In this case, my Vgd is my Vgs minus Vds, we have found here, right, we have found, let us say equation 1. So, we have found from equation 1 that Vgd is nothing but Vgs minus Vds, right, but my Vds here is what, case 1, Vds is 0 volt, Vds is 0 volt. So, I can write Vgd should be equals to Vgs, because my Vds is 0 volt, right. That means width of depletion region will be uniform, correct. Now, if my threshold voltage is 1 volt, Vgs is 2 volt, then my Vgd will also be 2 volts. So, width of channel will be the excess voltage, and excess voltage is nothing but Vgs minus Vt, which is my 2 minus 1 is 1 volt, very easy, right. See, what is the condition here? Condition here is, if I have a threshold voltage which is 1 volt, and if I have a gate to source voltage which is 2 volt, right, sorry, and I want to measure the width of the channel. So, width of channel is nothing but whatever the excess voltage is there, right, then only the channel will form, right. So, what is the excess voltage here? Vgs minus Vt, Vgs minus Vt is what? Vgs minus Vt is 1 volt. Because of this 1 volt excess voltage, there will be formation of the channel, or this will be the width of the channel. Similarly, if I have Vgs equals to 3 volt, right, then and Vt equals to 1 volt, in this case my excess voltage will be 2 volts, and that will be my width of the channel, correct. So, case 1 we have considered when Vds equals to 0 volt. Let us see case number 2. Case number 2 is Vds is not equals to 0 volt. In that case, what will happen? And Vds is greater than 0 volt. Not only it is not equal to 0, it is greater than 0. So, in this case Vgd, this equation is again equation number 1, right, this one we use this equation. In this case, since Vds increases, because Vds is greater than 0, right, Vgd would decrease, correct. If Vds increases, Vgd would decrease, and this Vgd reduces, which implies that drain is becoming more positive than gate. If drain is becoming more positive than gate, then depletion region will not be uniform. Easy, very easy, right. See, again let us see this condition, its condition, see, so easy. You have this Vgd equals to Vgs minus Vds, but if I keep on increasing Vds, then what will happen? If I keep on increasing Vds, my Vgd will keep on decreasing, right, easy. Now, if my Vgd keeps on decreasing, that means my drain is becoming more positive, Vds is becoming more positive, right, and Vgd is going down. So, that means drain is, because Vgd is nothing but Vgd is Vg minus Vd, right. Vgd is nothing but Vg minus Vd. If my Vgd is going down, that my drain voltage is getting positive, becoming more positive than gate. In this case, depletion region is not uniform. In this case, depletion region is not uniform. Let us consider then case number 3. Let us consider case number 3. In this case, what we see? We see that Vds is equals to Vgs minus Vd. Now, this is another case, right. in this case if VGS equals to VGS minus VD, then we have this formula again equation number 1, which was VGD equals to VGS minus VDS. If I substitute value of VDS, which is right over here, then I have VGD equals to VGS minus VGS plus VD, this is gone. So, VGD will be equals to VD, and this is nothing equal to threshold voltage. That means that channel width will become narrower, and this happens only near the drain, correct. What you understood is that from this equation, if I consider this particular case, then I have VGD equals to VT, right, and in this case what will happen, because my VGD is equals to VT, the channel width will become narrow, and this will happen near the drain, and you can see here the channel width near the drain will become narrower. When this becomes narrower, that means that my current is kind of reaches constant, my current reaches like constant, right, and this particular voltage is called pinch off voltage, as if I am pinching off. When you pinch something, it stops flow, it remains there, right. So, this looks like we have pinched off, it was increasing, certainly pinch off voltage required, and it start saturating. So, it is also called VD saturation, right, voltage is also called VD saturation or VD set. Okay. So, when VD set will occur? VD set will occur when you reach the condition VDS equals to VGS minus VT. So, we have seen 3 different cases. Case 1 was VDS not equals to 0, right. Second case was VDS is not equals to 0 and greater than 0. Third case is VDS equals to VGS minus VD. Okay. Now, if I want to understand what is the drain and transfer characteristics of an enhancement type MOSFET, if I want to understand what is the drain and transfer characteristics of an enhancement type MOSFET, let us see. Okay. Now, we know that output voltage is VDS, output current is ID, and control variable is VGS, because if I keep on increasing VGS, my current increases, correct. So, control variable is my VGS. Now, drain characteristics ID versus VDS for various levels of VGS, okay. That is we have to see. Now, VT and constant K is already given, that means that we already know what is value of threshold voltage is already there. Now, what we have to do is consider different cases, alright. First case is that VGS is greater than VT. When your gate to source voltage is greater than your threshold voltage, what will happen? Effective, V effective is nothing but VGS minus VT, right. Now, we know that VDS equals to 0 implies current equals to 0, right. When you apply VDS equals to 0, that means if I do not apply anything here, if I apply 0 voltage here, you see in the left side, right, then the current will be 0, it will not flow, right. But if I increase VDS, my current will start increasing, right. So, and it will increase until a voltage which is my pinch off voltage that we have already seen, right, and my current will become constant, my pinch off voltage is nothing but my VD saturation. This is easy, right. Case 1 VGS greater than VT, V effective is VGS minus VT, VDS equals to 0, ID equals to 0, VDS increases, ID increases, and VDS equals to VD saturation, that is my pinch off voltage. In this particular condition, if my VD saturation or VDS is VGS minus VT, what will happen? Let us see. Okay. So, here if I apply Kirchhoff voltage law, for this particular circuit, what will I have? VDS, we start from here, okay, VDS, and in this direction like this. So, VDS plus VGD minus VGS equals to 0 implies VGD is VGS minus VDS. This is similar condition, right. In pinch off voltage, VDS is VGS minus VT, we know that, right. In pinch off VGS will be VGS minus VT, right. So, in pinch off my voltage across drain and source, VDS would be equals to VGS minus threshold voltage, then my pinch off will occur. In this particular condition, I have VGD equals to, so I will substitute this value in this particular equation, okay. So, VGD is equal to VGS minus VGS plus VT, this gone, VGD is nothing but my threshold voltage VT, right. So, width of channel looks like is reached to 0, width of channel, it goes on decreasing. So, from here it will go on decreasing, it will decreasing, and then it will reach here. What you can see here on the left side, what I have drawn, you see, right, it looks like it is approaching 0, and that is why ID would be ID saturation. Now, you see VD set equals to VGS minus VT, we know that, right. So, if I apply, keep on increasing my VDS, I can see change in my ID. So, I keep on increasing my VDS, you see I can see change in my ID, right, but that cannot reach, that also has to depend on my VGS, that also has to depend on my VGS, right. So, I have VGS equals to 1, VGS 2, VGS 3 to VGS equals to threshold. So, above this value where VGS is greater than threshold value VT, above the value here the bottom where VGS equals to VT, as soon as VGS is greater than VT, my current can start flowing. We have seen this in the first slide, right. That means on increasing voltage I can see change in increasing current or depending on how much VGS we are applying. So, if I keep on increasing my VGS, I can see the higher current we can obtain, and this particular region you see that there is a saturation or pinch off region, right. So, if we keep on increasing VD saturation, if I keep on increasing this VD saturation, right, it will cause a breakdown for a particular value of VGS. Let us say VGS is, let us say some constant x, right, we have VDS, we have ID. So, if I keep on increasing VDS, what I will see is that my current keeps on increasing, this is VDS, this is ID. If I keep on increasing my VDS, then what I will see? I will see the change in the current depending on the gate voltage, and then it will keep saturating VGS, it will reach here. Still I keep on increasing VDS, then suddenly you will see that it starts breakdown. Suddenly the current shoots up, and this is my breakdown condition. Alright, and my MOSFET can be damaged, would be damaged. So, what we understood is that for a constant VGS we can apply VDS, but if we exceed certain voltage of VDS we may see the breakdown effect, Okay. So, now let us see another case. We have seen the first case, right, where we have considered that VGS is greater than VT. Let us consider second case where VGS 2 is less than VGS 1. Okay. VGS 2, which one VGS 2? This red color here, the line which is shown by brown color or red color is VGS 2, and this line is your VGS 1. Okay. So, let us this case consider VGS 2 is less than VGS 1, that means channel at VGS is channel width, right. If I increase channel width, my conductivity would increase or my resistance would decrease. Now, when VGS is less than VGS 2, that means my resistivity at 2 is less than resistivity of 1, or R2 is greater than R1, right. So, what will I have? VDS equals to VGS minus VT, and then we have nothing but, since VGS is less than VGS 1, that is why slope 2 is less than slope 1 and early pinch off will occur. Let us see once again. What does that mean? That if I have this particular equation where my VGS 2 is less than VGS 1, that means I see that the resistance at 2 is greater than resistance at 1, right, because the gate to source voltage is more. That means that what will I see is the current at VGS 1 would be higher, because resistance at 1 is lower compared to resistance at 2. Resistance at 2 is higher, that is resistance because of VGS 2, the resistance would be higher compared to resistance 1, that is why my current would be higher in case where I am applying VGS VGS1 and when I am applying VGS2 my current would be less. You can see here from the graph also that for different value of VGS I have different value of current, right. This VDS since VGS is less than VGS2, so what will happen, early pinch off. So, you can see here my pinch off happens early compared to VGS1, my pinch off happens early compared to VGS1, right. Now, if there is a saturation region, what is saturation region? So, when my VDS is extremely high, I told you, right, when we reach VDS extremely high greater than VGS minus VT and my ID equals to K times VGS minus VT whole square, then what will I have? My K is nothing but this particular value. Now, we are not interested in deriving the equations, okay, not in detail deriving equations. So, right now you just understand that if this is the equation given to you, what you can understand from the given equation, that is the idea, not to really derive the equation. We will see 1-2 derivations later, but right now if you are given an equation, from the equation can you understand what is the drain characteristics, if I change the drain to source voltage, if I change gate to source voltage, how the overall things would happen, how the performance of the MOSFET is going to change, that is the idea. Okay. So, if we go back to the screen, what we see is the saturation region VDS greater than VGS minus VT, ID equals to K times VGS minus VT square, K is constant and depends on the W by L ratio, W by L ratio is of channel ratio, then and I have K equals to constant K equals to ID on upon VGS on minus VT on VT whole square, which is given in amps per volt square. Now, I want to see triode region, right, the region on the left side. So, if you consider this particular graph, what do you see? Voltage VDS versus current ID, voltage VDS versus current ID. What we see that it keeps on increasing for different value of VGS, right, for different value of VGS you can see different current. Here what we see is that if you see the pinch off voltage and if you draw a line which interconnects the pinch off voltage back to here, everything on the left side of the VDS saturation, everything on the left side of VDS saturation is your triode region, okay, and VDS is less than VGS minus VT. So, we can write ID equals to 2 times K VGS minus VT into VDS minus VDS whole square by 2, right. We can write ID equals to 2 times K VGS minus VT into VDS minus VDS square by 2. What if we consider cutoff region? Where is the cutoff region here? Yes, you got it correctly. Where is it? It is right over here. It is in this region. So, when VGS is extremely less than VT, VGS is less than VT or less than equal to VT, we have current ID equals to 0. You can see here the current is 0, right, because my VGS is equals to threshold voltage or is less than threshold voltage, is equal to or less than threshold voltage. Okay. Now, let us see the transfer characteristics. Of the n channel MOSFET. So, what we see here, you see this one right side, see the right side. Okay. What I have? I have VDS and I have current here ID, Now, this graph you already know, right, for different value of VGS. So, assume that my threshold voltage VT equals to 2 volts. I am assuming VT equals to 2 volts, then my gate to source voltage, that means my VGS should be greater than 2 volts, right. So, what I see here at VGS equals to 2 volts, 3 volts, 4 volts, 5 volts, 6 volts, 7 volt, 8 volt. For increasing VGS, I can see increasing my drain current depending on increasing of my drain to source voltage. This is the graph, right. If I want to draw the transfer characteristics, it is very easy. You have to draw ID versus VGS, ID versus VGS, that is a plot that you have to draw, right. Now, you write down value of VGS from 0 to how much you have applied 8 volts you have applied. So, 0, 1, 2, 3, 4, 5, 6, 7, 8, right. Then what you do? Then what you do is you connect this VGS value, this 0 value, right. Where is 0? 0 is connected here. Where is 1? So, if you see VGS equals to 4 volts, right. So, 4 volts we have to, 4 volts is here, right. Where is 5 volts? 5 volts is here, right. Where is 6 volts? 6 volts is here, right. So, if I connect like this, you see I have current here, right. I have current here, I have current in both the directions, in x and sorry, I have current in both the plots in y direction, here and here I have current, right. So, I am just joining current line 10 with 10, 9 with 9, sorry, 9 with 9, 8 with 8, 7, you can see 7, then we have 6, we have 5, 4, right, we have 3, we have 2 and we have 1, right. I have joined the current axis because both y axis are ID. This is easy. Now, what I have to do? I have to just find out the voltage. So, voltage VGS equals to 3 volts. For VGS equals to 3 volts, right. Where is it? VGS equals to 3 volt, somewhere here. For VGS equals to 4 volt, somewhere here. 6 volts here, 8 volts here, 9 volts here or 7 volts here. So, now I have to just join lines like this, see. So easy, right. So easy. If you know ID versus VDS, you can find ID versus VGS. If you know ID versus VDS, you can easily find the drain transfer characteristics of ID versus VGS, right. Easy, very easy, right. So, again if you want to understand quickly what we have done, here is that we have drawn the ID versus VDS plot. Now, I am drawing ID versus VGS plot. For drawing ID versus VGS plot, first thing I will do is I will correct the current lines in both the plots like this. Right, this is I have done. Now, what I will do? I will draw a line from 1 volt onwards. Okay, 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, 7 volt and 8 volt. What is this volts? This is my VGS. Now, this much is easy. Now, what I have to do? I have to see VGS equals to 3 volts, right. For VGS equals to 3 volts, my current is 1. So, I will just put a mark here. Then another one, VGS equals to 5 volts, my current is about 2. So, I will mark it here. VGS equals to 6 volts, my current is about 4, right, 4 or yeah it is 4. So, I will again put a mark here. Then my VGS equals to 7 volts, my current is about 7 milliampere. So, I am marking about here. When my VGS is 8 volts, my current is about 10 milliampere. So, I am marking again here. Now, if I join this all the marks, like this, I have my characteristics. I have my transfer characteristics. Easy, very easy, right, very easy. Now, in triode region is nothing but your ohmic region. Saturation region, you know, VDS is greater than VGS minus VT and ID equals to K times VGS minus VT whole square. Okay. And then there is cutoff region. So, while obtaining transfer curve, only saturation regions are saturation levels are employed, because ID equals to K times VGS minus VT whole square. So, we will not have any linear curve, Okay. So, this is your transfer characteristics of the n channel MOSFET. Now, in the next module, we will see what is the depletion type MOS transistor, depletion type MOS transistor. That we will continue in the next class. Right now what we have seen? We have seen that if you are given an n channel MOSFET and enhancement type MOSFET, how the MOSFET will operate, how can we understand the different cases when we apply different drain to source voltage, what about the drain transfer characteristics for the enhancement type MOSFET, how we can derive this drain transfer characteristics curve, and when we consider different value of VDS, when we consider different value of VGS, and what are the saturation voltages, what are the cutoff voltages, what is the triode region, and how can we plot the transfer characteristics if you are given the ID versus VDS plot. Then we know that ID versus VDS plot in enhancement type can be generated by applying different gate to source voltages. So we can have ID versus VGS plot, and we can connect the current lines, and then we can draw vertical lines for the gate source voltage, and then you can see for gate to source voltage in my ID versus VDS what is my current. According to that I will put the current in my ID versus VGS plot. This is how I derive my transfer characteristics for the enhancement type MOSFET. Okay. So now you have not only seen that how you can fabricate a n channel enhancement type MOSFET or n channel MOSFET, you also know. So when I talk about fabrication, it is not actual fabrication, not experimental way, but at least you have seen on theory that how you can design the process flow for fabricating a MOSFET. And then we moved on to the to this particular lecture, where now you have seen how the enhancement type MOSFET would behave and what are the transfer characteristics. Next time, in the next lecture, what we are going to see? We are going to see the depletion type NMOS transistor, and again we will see the construction to the drain characteristics. Okay. So this is not an this will not be a next lecture, it will be part of the same lecture but a next module. So till then you just look at the things that I have taught you, and I will see you in the next module. Take care, bye.